Today we are learning about solvent effects on your chemical reactions. That's right, in this video we're talking about solvent effects, and in particular we're going to be looking at solvent effects on reactions. So first, let's just get a baseline of solvents. Many of you have seen things about solvents before, so we're just going to review a little bit. Then we're going to look at the solvents we're going to be most likely to use and why we're using them. That way, when you're deciding what you should use in your reaction, it makes sense why certain solvents should be used. With solvents, there's the two main categories, which is polar and nonpolar. Things start to get trickier as we go on. This is the first one you want to look at. Is my solvent polar or nonpolar? And when you think about a solvent that's polar, right away your brain probably goes, water is polar. Bingo. And when we think about solvents, we think about likes dissolving likes. So something that could also be miscible in water, like ethanol or alcohol, any alcohol really, these are also very polar. Nonpolar solvents are things that don't dissolve in water. So think of anything like an oil. So we can draw alkyl chains. All of these are nonpolar. So this one was just hexane. You could think about benzene being nonpolar. There are two factors that describe the polarity of a solvent: their dielectric constant and their dipole moment. The dielectric constant is actually describing the bulk solvent. So when you think dielectric constant, think a lot of molecules. So we're looking at many, many molecules together. And when we think about the dipole moment, we're actually just looking at one molecule. So it's the individual molecule. Let's look at a couple polar solvent examples. We're going to list our favorite one, which is water. And the dielectric constant for water is pretty high. It's 78. And its dipole moment is 1.9. Now for acetone, this is another pretty common polar solvent, okay? And acetone has a dielectric constant of 21, and its dipole moment is 2.7. Now let's draw in our dipole moments on this molecule. So again, dipole moment is just for the individual molecule. So we know oxygen is electronegative, and so the dipole moment would be going towards the oxygen. And hey, we can also describe this with resonance. We know that our resonance arrow would show that oxygen pulling electron density towards it. So it's something to keep in mind here that we can use resonance to help explain these dipole moments. Now, when we think about water, we know oxygen is more electronegative than hydrogen, so the dipole moment is going again towards the oxygen. And one thing I want us to note is that the dipole moment for acetone is higher than for water. And this kind of makes sense because we can actually draw a full-blown resonance structure showing that this oxygen is really accepting these electrons. Hybridization has a big role here in this difference in dipole moment. Now, the key here is that their dielectric constant is very different. Now, both of these are considered polar. Polar typically has a dielectric constant, typically, of greater than 15, okay? Now, what would make these two so different? Well, think about this. The dielectric constant is the bulk solvent, okay? And when we think about polarity, and when we talk about polarity, we're talking about the ability of a solvent to separate ions from each other. So I'm going to write this down here. Ability of solvent to separate ions from each other. So the key takeaway here is that both of these values are important when we're deciding if something is polar or nonpolar, and there is a range of polarity. The key here between these two is that water can be involved in hydrogen bonding. And we'll talk more about that. But that's why water is so good at separating ions compared to acetone. But again, they're both considered polar. See how this can get really confusing. So what I want to do now is I just want to give you a list of solvents that are ones that we definitely use in lab. I used to be a synthetic organic chemist working for a pharmaceutical company, so I can tell you the ones that I love and the ones that you're going to see most often, okay? So let's list out some solvents. I want to first note that there is one more degree of separation for solvents. We use words called protic or aprotic. Protic solvents simply mean they have the ability to hydrogen bond. Aprotic means it cannot hydrogen bond. So let's write that out. Protic. H bonding can occur. Aprotic, no hydrogen bonding. For polar protic solvents, these are some of what we already talked about. Water is a great polar protic solvent. You can think of any of your alcohols that you've used before. Formamide and formic acid are also considered polar protic solvents. Polar aprotic are solvents that are polar, but there's no hydrogen bonding. These include acetonitrile, okay? You can also have DMSO. Which is dimethyl sulfoxide. You can also have DMF, which is dimethyl formamide. I want to highlight here really quickly that the big difference here between this formamide here at the top and dimethyl formamide is we don't have any of those NH bonds. See how we took them away? Polar aprotic means no hydrogen bonding. So these are three really common solvents where they don't have any hydrogen bonding, but they're also polar. Okay, now we get into the borderline ones. And these get interesting because they still have the ability to help separate ions from each other in solution, but not nearly as well as the polar aprotic. So if I were to draw an arrow on this slide as we continue to go through, we're going to write ability to separate ions. To separate / stabilize ions. The borderline ones can still do it better than fully non-polar solvents. And the way that they get around it is, I'm going to draw an example here. This is a cyclic ether. This is THF, or tetrahydrofuran. And this has lone pairs here that can donate and can help stabilize charges. So many times these borderline ones have donor atoms, or they can donate electron density. Donor atoms. So think about THF, that's a really common one. Diethyl ether. Really great solvent here. We're going to use this a lot in our class as well. And then also ethyl acetate. So these donor atoms here have lone pairs that can help stabilize charges. Now, also kind of right underneath the borderline is one of my favorite solvents, CH2Cl2. This is dichloromethane. Now, all of the borderline and below are considered nonpolar. But they have characteristics that to some extent can help them stabilize charges. Dichloromethane is also a really great solvent. Now, we know dichloromethane isn't completely void of a dipole moment, because if we draw it out, check out the dipole moment that we have here between the carbon-chlorine bond. But it's pretty close. Carbon-chlorine bonds are here, but it mainly has CHs. So now we get into the nonpolar, which are the most boring solvents ever. Well, I would say I'm kidding, but I'm not. Hexane, nonpolar. Benzene, nonpolar. So why do we care so much about solvents? Well, when you think about a reaction, many times we're making high energy intermediates. Okay, we want to stabilize those high energy intermediates. So we might try to use something that's more polar that can stabilize and separate the ions or the partially charged transition state. Now, the issue comes in when we have a solvent that stabilizes something too much. Okay, so they're on this continuum of ways that we can help enhance our reaction. And in some cases, certain solvents can absolutely kill your reaction. Let's take an example that we've gone over before. Let's do an SN2 reaction here. We're going to do this reaction in the presence of DMSO. Now, when we think about the mechanism here, we know that we're going to attack the back side of the carbon with the leaving group. And this is going to go through a transition state that has the bond breaking between the carbon and bromine, and then we have the bond forming between our sulfur and the carbon there. This is our transition state, and we know that our product... Now, the chirality doesn't matter here because we don't have a chiral center. But what I want to show you here is this transition state. So let's kind of walk through what's going on here. We know that we have a partial negative on our leaving group and our nucleophile. See, our nucleophile was negatively charged. As it starts to attack, the electrons are going from the nucleophile to make the new sulfur-carbon bond. That carbon is losing the leaving group. That means it's partially positive. So in our transition state, we have these partially charged species, okay? And we know for our SN2 reaction, it's bimolecular. So we have our starting alkyl bromide plus our nucleophile. The transition state is up here, okay? Now, if we can add a solvent that can help stabilize some of these partial positive and partial negative charges, what's going to happen is that we're going to essentially lower the activation energy for the formation of that transition state. Think about solvent molecules as just kind of helpers in this case. DMSO is great for this because if I draw the resonance structure of DMSO, we can fully see how is this able to help support these partially positive and partially negative charges. So what's going on here is we have these interactions between solvent molecules and our reaction. So on this top reaction, we're doing an SN2 with a polar aprotic solvent. SN2 reactions prefer polar aprotic solvents. Let's see what would happen, though, if we used a polar protic solvent, something that could do hydrogen bonding. We're going to draw the same reaction. And we're going to use methanol. Now, nominally, you can draw the same reaction mechanism here, where we have attack and this carbon with the leaving group. The leaving group then will leave. But check this out. SN2 reaction with a polar protic solvent. Now, I talked about these solvents stabilizing these charges in transition states, but there can be a negative effect if you have too much stabilization, all right? We want the solvent to support some of the charges that are happening, but we don't want it to inhibit. So we're going to draw out our thiolate here, and we have our sodium hanging out here. And then we have tons and tons and tons of methanol. I'm going to draw a whole lot of random methanol molecules. We draw things on 2D pieces of paper and forget how freaking messy they are. Okay, so this sulfur here has a negative charge. Methanol can undergo hydrogen bonding, and that's going to happen with the sulfur. In fact, probably too much so. Now, sodium is stabilized by the lone pairs here on this oxygen. Okay, well, that's kind of interesting. Now, here's the problem. Because it's a polar protic solvent and we have H bonding or hydrogen bonding, this makes this nucleophile just completely smothered in hydrogen bonds, okay? Think of the nucleophile trying to move through this reaction and it can't, okay? It's like trying to move through quicksand. This nucleophile is completely covered in quicksand, hydrogen bonds. So polar protic solvents are not good for SN2. They slow down the nucleophile. They are too good at separating charges in solution. So let's write something together here on the top. SN2, you're going to typically see polar aprotic solvents being used. Crown ethers are cyclic ethers containing several oxygen atoms. They can bind to metal ions in non-polar solvents and essentially make ionic compounds soluble in non-polar solvents. Here I have an SN2 reaction with an alkyl bromide with sodium cyanide in a non-polar solvent, benzene. The outside of our crown ether is very non-polar, and so the sodium metal ion binds in the middle of our crown ether, and they're called crown ethers because they look like crowns. And check this out, the cyanide anion is a naked nucleophile hanging out in non-polar solvents. This makes this SN2 really, really fast. And this is one way we can use solvent effects to our advantage. Let's go over SN1. So for an SN1 reaction, we have our carbon with our leaving group. And then we typically use a nucleophile that isn't that great of a nucleophile, but it's not a good base. Otherwise, we could get E2. So let's just focus on SN1 now. So we have water here, and we've got a good leaving group on our alpha carbon. We're going to make a tertiary carbocation. I've drawn equilibrium arrows to show that this is reversible, that bromine can come back and attack. And then we're going to have water attack. Oxygen atoms. They can bind to metal ions and non-polar solvents. Remember, always start your electrons or your arrow here at the electrons. We're going to attack the carbocation. You've probably drawn this mechanism, and guess what? Practice makes perfect. All right, now our solvent here is water, and we have tons of it. So we're going to take another water molecule, and we're just going to deprotonate. You want to isolate something neutral so that you can analyze it. Alkyl bromide and so now we end up having our desired alcohol. The outside, draw a longer arrow. Okay, so we have our starting material and we have our product here. We're using water, but we're also using water as a nucleophile. This is where things get more confusing because you're like, wait, what is my solvent? Well, your solvent is water, actually. You just add tons of it. Okay? So in cases like this, sometimes your solvent, this is one way we can use solvent effects to our advantage. Can be your nucleophile. In the case of SN1, this is typically the case. Now I want to focus on this carbocation here. Now we have water present, and water, as we've learned, is a polar protic solvent, so it can do hydrogen bonding. Now, why is this so important? Well, if we have lots of water molecules around, we're going to be stabilizing this positive charge. This is a really good Lewis acid, and it's very high in energy. So in SN1 reactions, we make a very high energy intermediate, the carbocation. So for SN1 reactions, we need more stability. We need to be sure that we can actually make the carbocation. By having a polar protic solvent in SN1 chemistry, this is going to lower the energy of that transition state so that it's a little easier for it to form. So for SN1 chemistry, you're going to be using polar protic solvents. Let's discuss briefly E1 and E2. Now for E1 reactions, we're typically using very acidic mixtures in water. So these polar protic solvents are good. And then for E2, we require a very strong base. Now for E2 reactions, we're typically doing them in polar protic solvents as well. Notice, and you'll see this more and more in your organic chemistry courses, but when you have a base, it typically matches the solvent, which is the proton there, okay? Now, this doesn't matter as much compared to the SN2 because really we're trying to do an acid-base reaction, and it's really the strength of the base that dictates whether or not you do an E2 reaction. What I want to highlight here is that solvent effects are real and they are important and they can affect the rate of your reaction. So for E2 reactions, you also are typically going to see polar protic solvents. Now, I want to say this one thing. Please don't just memorize this. Understanding what the solvent is doing is going to help you so much more later on in your organic chemistry career. If you just memorize which solvents go with what, you might get tripped up when you see different solvents that could actually behave similarly. I gave you a spectrum of solvents in the beginning of this lecture video because I wanted you to see that it's not just one way or the other. Many times when we're running reactions, we have to use a mixture of solvents because we're actually trying to get our starting material in solution, okay? And sometimes we'll sacrifice a rate of a reaction just in order for the reaction to be able to go, okay? So don't memorize this. I want you to understand the concept of why we're doing this and understand polar protic, polar aprotic, and which ones can't hydrogen bond. These are our borderline ones, but they do have these donor atoms that could help stabilize ions in solution. All right, that's it for this video, and I will see you in the next video.